So before, because time may get short, I want to start with the most important, slide, in fact, which is the acknowledgements to my fantastic group of students. And in particular, a lot of the work that I'm going to present has been led by Yuan Zhao. He will give more details about all of this tomorrow, Thursday, 4:54. I know it's the end of the day, but try to make it if you want to get some more details and extra data that I'm not going to be showing today. Okay, we have really a lot of data. This has also been part of the work in collaboration with Ray Ashuri and with Jason Liu, Javier Sanchez, Ahmed Emir Spencer. Most of them are here. We also have our collaborators at Harvard, Tim Caxias and Xian Fang. We enjoy, of course, the wonderful hexagonal boron nitride from Japan and our funding agencies. So a lot of you, this is the APS March Meeting, you know that among the most fascinating states of matters and materials are those where interactions between electrons are very strong, okay? This causes electronic behaviors which are very unusual. For example, you have heavy fermions where electrons have effective masses of hundreds or even thousands of times the bare electron mass. You have also systems like the quantum spin liquids where your spins, even if you cool down to 0 temperature, they end up not ordering and they're fluctuating, wildly in your system. And perhaps the most famous of these strongly correlated quantum materials are the high temperature superconductors, where we have this phase diagram of temperature and doping with superconducting dome and all kinds of strange phases which we do not fully understand yet. Now, this, just to put everybody on the same page, let me remind you all, I'm going to go quickly, through what's our understanding, from a single particle point of view of what metals and insulators are. So, if you have a density of states and you have bands, if you occupy fully one band and the next one is empty, that's an insulator, that's a band gap. If you have a band which is partly occupied, now your electrons can access, at very low energies, they can access available states to conduct electricity, and that's a metal and it conducts. Now, sometimes you have this situation where something that should be a metal, because you have just partly filled your band, actually becomes an insulator because of the strong interactions between these electrons, which are in this material, okay? So a gap opens, and you have a realization of something like, a full band and a totally empty band. So you got into an insulator, but this occurs in a situation in which you should have a metal, and this is a correlated insulator. Now, one of the most famous examples of this are Mott Insulators. So if you have, for example, here a square lattice of atoms, and I put 1 electron per atom. Usually I can put 2 electrons per atom, spin up and spin down. But now I'm only putting half of the maximum amount of electrons that I could put in this band. Okay? Then this thing, normally, because this electron can jump here, it would conduct, it would be a metal that would be able to conduct electricity, just electron jumping, through the different sites. However, there are materials where the interaction between these electrons are very strong, repulsive interactions. So this process is actually not allowed. You don't have this double occupancy allowed. So that means that all of the electrons remain stuck in their positions because they cannot jump from atom to atom. Okay? And that forms this correlated insulator. It occurs precisely when you put half, when you've half filled your band, when you put half the total amount of electrons that you could put in a band, then this insulating state appears, and it's kind of unusual. Now, the Mott Insulator state is the parent compound for stoichiometric high temperature cuprate superconductors. You have these copper oxide planes. If you grow them without any doping, you actually have a Mott Insulator. Okay? And if you now remove electrons or add electrons to this Mott Insulator, then you have now this competition now because you have an empty site. These electrons now can actually move. Okay? You still have to pay charging energy if you want to move into some of these sites. So now there's a competition game between kinetic energy and Coulomb repulsions. And it turns out that a superconducting superconducting dome appears upon doping sufficiently, and all other kinds of strange physics appears in this situation. This is something which is typically modeled with the so-called Hubbard model. Okay? It's a model that we cannot solve analytically, perfectly, theoretically. Okay? And as a result, there's a lot of, for 3 decades since cuprates were discovered, and this model is also used for many other correlated materials. We're struggling to fully understand the physics in this phase diagram because theory is limited in how much they can calculate exactly. So because of these reasons, they have alternative approaches to try to investigate the physics of correlated quantum materials. Okay? And one of the most exciting and successful approaches is that of using ultra-cold atoms in optical lattices. So it turns out that people have thought, okay, these materials, cuprates and others, are so complicated, all this chemistry, this dope and so on. Let me try to simplify the problem tremendously. Let me just make an optical lattice, and I'm going to load one atom into each of these minima potential minima in the optical lattice. I have full control with my lasers over the interactions and all the parameters of the system. And then, for example, what people were able to realize already about 16 years ago is the transition from a Mott Insulator to a superfluid as they vary the interactions. This was done with bosons, with atoms which were bosons. A few years later, people realized this with fermions. So they realized the Fermi-Hubbard model. And there has been tremendous progress recently in realizing this. They have been able to reach antiferromagnetism in the Fermi-Hubbard model. Okay? So that means that they have been able to explore initially this corner. Now they're exploring this full corner of this phase diagram. But there are significant problems in order to cool down enough to reach, for example, D-wave superfluidity in these systems. So we have these two platforms, the actual quantum materials, where length scales are typically an angstrom or so, and energy scales are of the order of 100,000, 10,000 Kelvin. We have these other cold atoms in optical lattices, where length scales are of order a micron, much bigger, but energy scales are also much smaller, about a nanokelvin or so. And what I want to tell you about today is about this platform that we have created, which is called magic angle graphene superlattices, where the length scales are intermediate, about a factor 100 from each of these. Okay? This lattice scale is about 10 nanometers. And the energy scales are also intermediate, of order of 110 Kelvin. So with this is what I'm going to be telling you about. I'm going to tell you a little bit about Legoland, twistronics, and magic angle graphene. Then I'll tell you about Mott-like insulated behavior at half filling. Then an unexpected surprise, which is no longer so unexpected, because all of you are here. And then if time allows, I'll mention a couple of words about where is this going. So, there have been, as you know about, when graphene was isolated, and investigated, very deeply and vastly by many groups after, 2004, 2005. People realized that actually this is just one example of many materials, that we can, many 2D materials that we can isolate. And in fact, we can stack them on top of each other. So this, brought comparisons to, welcome to 2D materials Legoland, and you have these reviews by my friends and colleagues where, they emphasize the fact that you can stack anything on top of anything, and this has fantastic properties. Now, if you have played with Lego, you realize that something that you have to do with Lego is you have to stack them precisely on top of each other, right? You cannot rotate two Lego pieces and stack them, right? So in my opinion, this is all, of course, great, but it misses one of the most fundamental and unique aspects of van der Waals materials and heterostructures, which is the fact that these materials can be rotated arbitrarily on top of each other. This is something unprecedented. This could never be done before. It cannot be done with semiconductor-grown MB-grown semiconductor heterostructures. It cannot be done with bulk crystal growth. This is something which is unique to van der Waals materials. Okay? So, and we can stack them at will. Okay? So let me stop this before you get sick. And so what happens, I'm going to tell you today about the simplest possible twisted van der Waals heterostructure, which is I'm going to put graphene on top of graphene. Yeah? And then I'm going to rotate the system. So I have here graphene. You all know the electronic band structure of graphene. These linear Dirac cones. This is real space. This is momentum space. So now I'm going to put another layer of graphene on top. And now I'm going to rotate it. Okay? So if I rotate it, and sorry, the simulation goes slow here. If I rotate the real space lattices, the reciprocal space lattices also rotate. Okay? This leads to separation in reciprocal space of the Dirac cones of these two sheets. Yeah? So this thing it goes as the sine of the angle. For small angles, goes as the angle. So twisting leads to layered Dirac cones, which are separated in momentum space. Now let me go from a large twist angle, and now let me rotate towards small twist angle, and let's see what happens. So we have here, these two Dirac cones. Now it's a small angle, so the separation in momentum is proportional to the angle of rotation. If these two Dirac cones from these two sheets, so if the two sheets did not interact with each other, we would just have Dirac cones that cross each other. Yeah? Now, in reality, there is interlayer coupling. Okay? These two layers talk to each other. And therefore, what happens is that there is a hybridization here, where these Dirac cones cross. There is level repulsion there. There is a band opening there, okay, of a gap opening. Now, this is for angles which are relatively large, such that the height of this crossing is much larger than this interlayer coupling. However, if I now decrease the twist angle, you can imagine that as I take these two Dirac cones, which are crossing here, and I make them closer and closer, this opening of a gap flattens the bottom band such that you realize a situation like this. Okay? When your interlayer coupling is very similar to that crossing point, you have a flat band now. Okay? This flat band condition, okay, is reached at the so-called magic angle, a term coined by Bistritzer and McDonald. Okay? And it depends on what's the interlayer coupling between these two sheets. So for graphene on top of graphene, this magic angle happens to be 1.1 degree. Okay? At that value, you reach a flat band condition. So let me tell you now what happens in the evolution of the electronic structure as you are doing this process. Okay? So here I'm showing the two reciprocal spaces, lattices. This is the superlattice Brillouin zone. Again, because you have a long wavelength moiré pattern, you have a smaller superlattice Brillouin zone. In momentum space, you are small. It's this little hexagon here. Okay? So I'm going to show now a video of the evolution of the band structure, and you're going to see that this, as I rotate towards smaller angle, the moiré wavelength becomes larger, so the superlattice Brillouin zone becomes smaller, and you're going to see what happens to the electronic structure. Okay? As you can see, if you are at 3 degrees, which is a relatively large twist angle, what you see are Dirac cones stemming from the corners of the superlattice Brillouin zone. Okay? So let me show you now what happens when you twist the angle. As you see, the band structure is evolving. You can see now as we get towards lower and lower angles, this thing starts becoming very small bandwidth, and you're going to see a flattening, total flattening there at 1.1, flat pancake. Okay? If you keep decreasing, the thing evolves again. And actually, it keeps going. You can go to second magic angle, to third magic angle. Okay, it gets very complicated. Since my student put so much time into this, let me run it again. So you see there's an evolution of the band structure. The bandwidth is dramatically decreased as you are approaching the magic angle. Now you're going to get a flat pancake there at about 1.1 degrees. And then the thing continues evolving. So this magic angle happens at 1.1 degrees. Now, this is an actual cut of that band structure for 108 degrees. Okay? This is energy versus momentum. You see, this is not 100% flat, but the bandwidth has been decreased from several electron volts in graphene down to about 10 millivolts now. Okay? These bands are very, very flat compared to the original Dirac bands. Okay? So now, flat bands, so flat in momentum space, means actually localization in real space. Okay? So you have here the calculated density of states in these flat bands, and it happens that the density of states, electrons are concentrated in these AA stacking regions. Okay? So these regions are weakly tunnel coupled through the AB and B stacking regions. So what we have here is electrons, which we can load in this superlattice. The separation between these AA regions is 13.4 nanometers. So here you have your triangular, our triangular Fermi-Hubbard lattice, where we can load electrons and try to play with this. Okay? So now let me start showing you some data. Okay? So the devices look like this. We have twisted bilayer graphene encapsulated in hexagonal boron nitride. We have a bottom gate. We have source and drain contacts so that we can apply voltage and measure the current. With this gate electrode, we can control electrostatically the charge density in our system. Okay? And if you want more device fabrication details, et cetera, you can go to Yuan's session. So just a reminder, if you have regular graphene, just monolayer graphene, single sheet, okay? If you measure the conductivity as a function of density, what you have is, if your Fermi energy is deep in the valence band or deep in the conduction band, you have lots of holes or lots of electrons. It conducts very well. If your Fermi energy is at the Dirac point, it conducts very little because you have no carrier density. Okay? So this is what happens with single layer graphene. Now let's see what happens when you have these twisted bilayers as we reduce the angle of rotation. So I showed you first for 3 degrees. Again, this is just this V shape, which is representative of graphene. Okay? That's all that happens. I'm showing conductivity. I'll show real axis with units in a moment, okay, in the next slide. Here I'm showing conductivity as a function of density. I am normalizing the density by the full density of electrons that can fit in that band, in that flat band. Okay? So one means I'm putting as many electrons as they fit in this band. So if I now go to 1.8 degrees, it's not jet magic angle, but it's a small twist angle. The conductance as a function of density looks, near charge density still looks like graphene. However, it starts increasing, but we get an insulating behavior when we completely fill the band. Now, this is easy to understand. When you completely fill the band, then you have to go to the next band. There's a band gap there in between the two bands, so you go insulating. This is something that we more or less expect. The details are actually quite a bit more complicated, but you more or less can, you can easily imagine this. Okay? For details, you can go to this work, and it has been very, related work recently by the Tutuk group. Very nice work also. Now, let's go to the magic angle. So if now go to 1.08 degrees, what you see is you have, again, this V-shaped conductance near charge neutrality. You have an insulating behavior at full filling. But look, we have new insulating state when we put half the number of electrons that we could put in this system. Okay? This is something that should be a metal because it has a partially filled band, half filled band, but it's actually an insulator. So when we did this, we realized, and you can see now the actual conductivity with real units and density, okay? We saw these two insulating states, okay? And we realized immediately that these were very different from these other two insulating states or any other insulating states we had seen in graphene, bilayer graphene, graphene on HBN. There are many, many systems in which you can gap out graphene doing various tricks. All of those systems, this insulating behavior was very, very different. We immediately realized. One of the things that we realized is that it is, and by the way, this only occurs for angles which are about between, around 0.1 degrees around the magic angle. If you're 0.2 degrees away from the magic angle, all of this disappears. Okay? We never see this insulated state at half filling. So the first thing that we realized that it was kind of unusual is that this system exhibits a metal-insulator behavior. At high temperatures, it's a metal. At low temperatures, it's an insulator with an energy scale about 4K. This conductance is 1/T. Okay? So at about 4K, the system goes from a metal to an insulator. That's already unusual. All of the other insulating states is just insulator. Cool down, and it's always insulating. It doesn't exhibit this metal insulator behavior. But the most dramatic difference with respect to any other insulating state we had seen before, was the following. In a magnetic field, and it doesn't matter if it's perpendicular or parallel to the graphene system, in a magnetic field, but it's most surprising that it's in a perpendicular field, the system goes from an insulator to a metal. Everything in graphene, when you apply a magnetic field, goes from metal to insulator or from insulator to more insulator. Okay? Nothing goes from insulator to metal when you apply a perpendicular magnetic field. Okay? So this was really very surprising. And the way we understand this is the following. In a single body picture, okay, you have the two bands. You have no band gap because this is a Dirac system. When you are at half filling, you develop this many body gap state. Okay? It turns out that this system very likely consists of singlets, okay? Spin singlets. And when you apply a magnetic field, parallel or perpendicular, because the important thing is the Zeeman effect, you polarize these singlets, and when the Zeeman splitting, closes this gap, then you start conduction through the system. Okay? This picture, again, we have a lot more data that you can look at in the paper. It's supported by additional quantum capacitance measurements of the density of states, by quantum oscillation measurements, and by many other things. Okay? So you can look for details at the paper. So, and by the way, I was very happy to see that yesterday in ConMat, the group of Feng-Wan posted a related work, Mott Insulator behavior, on ABC trilayer graphene on HBN, which forms a similar triangular lattice with localized electrons, because ABC trilayer graphene has flat bands, which also lead to strong interactions. So this is a general platform that it's going to be possible to realize in many systems, as I will mention also at the end. So now, let's go to the surprise. So when we took this data, these were two terminal devices, okay? And then we will look, if we look at the temperature dependence here near, and let me remind you, from 0, if we go in this direction, we're putting electrons in the system. If we go in this direction, we're putting holes into the system. So we look at and by the way, notice that sometimes we have extra features at 1/4. I will show later at 1/4 filling rather than 1/2. Also at 3/4 fillings. Okay, there's a lot more than what I'm showing. So if we'll zoom in near this electron Mott-like insulated state, we have this conductance as a function of temperature. It just decreases, nothing too special, it's an insulator. But then when we looked near the whole doped Mott insulator state, yeah, what we saw is the following. Okay, at exactly half filling, the conductance decreases, it's an insulator, but hey, look nearby, this conductance sort of increases, okay? So we were like, can you imagine, that this would be something like, I don't know, superconductor? We were joking, So these were two terminal devices. So then I told, to my student, okay, let's make 4 terminal devices. Let's look more carefully into this. So we made 4 terminal devices. We first characterized them, again, in a 2-terminal setting, okay? So this is another device, 1.16 degrees, okay, rotation angle. This is in the presence of a small magnetic field, perpendicular magnetic field, and you measure the conductance as a function of density, okay? And you have the charge neutrality. You have deep at 2, at 3, and at 4 electrons, okay? Same thing, -2 and -3. If we now look near, okay, if we now take this trace, again, this is 2-terminal, at 0 magnetic field, you see that not too much happens here, a little bit, but not too much action. But here there's a dramatic increase of the conductance. This is, again, 2-terminal measurement, okay? If we actually now take 4-terminal measurements, what we get is that these devices superconduct, okay? This is the resistance as a function of temperature. These are 2 devices, 1.16 degrees, 1.05 degrees. The resistance goes to 0, decreases the resistance by 3 orders of magnitude below our noise measurement floor, okay? We can actually take the VI curves, at low temperatures. These are absolutely flat. We can do a standard test of 2D superconductivity. This thing very much superconducts. Now, the nice thing, remember, is that we have this gate voltage control with which we can continuously tune the density in our system. So when we zoom in actually around this area, this is what you see, okay? So this is the resistance as a function of temperature and density. Red means high resistance. Dark blue means 0 resistance. This is the half filling, this Mott-like insulator state. And if we dope with a few electrons, we have an electron dope superconducting dome. If we dope with a few holes, we have a hole superconducting dome. And we can do this continuously as a function of gate voltage in a single device, okay? This immediately, when we saw this, we were pretty stunned. This immediately, draw our attention, like the comparison with the phase diagram of the high-temperature cuprate superconductors, okay? Now, in the cuprates, for some reason, they choose hole doping in this direction, electron doping in this direction. Let me actually flip it for you, okay? So now we have a Mott insulator state at 0 doping, okay? So 0 doping means half filling for the cuprates. If we dope with electrons, we have a smaller superconducting dome. If we dope with holes, a more robust, a wider superconducting dome. You can see that we also have a smaller superconducting dome for electrons, a wider superconducting dome for holes, okay? But in order to do this in the cuprates, you need, first of all, different materials classes for electrons and for holes. And second, to fill this entire gap, this is always a theoretical phase diagram. Experimentally, you need a different crystal, a different growth for each point on this axis. So in order to do this in the cuprate, you need actually hundreds of crystals and hundreds of materials. And we're able to do this electrically because we have access, electrical control of our density. So, let me show you the data for the 105-degree sample. Here, the Mott insulated state is weaker, such that we actually can reach a metal to insulator to superconducting, transition. You have the electron dome, which is much smaller. There's a bigger asymmetry now. This has actually a much higher TC at optimal doping of about 1.7 Kelvin, okay? We seem to always have a more robust dome for holes than for electrons, very similar to the cuprates. But we can, of course, apply magnetic fields to these systems, okay? We can kill the superconductivity. We can look at this behavior as a function of temperature and magnetic field so that we can extract our superconducting coherence lengths. We can actually apply perpendicular and in-plane fields, okay? Of course, because it's a 2D superconductor, we can apply huge in-plane magnetic fields, as it has been shown earlier today by many people. In fact, we can do all of this continuously, again, because we can plot these phase diagrams, now perpendicular magnetic field and density. These are for the 2 devices, and you have these superconducting domes in this magnetic field density plots, okay? Now, when my students showed me this data, I was like, oh, you know, this is nice, but it looks kind of ugly compared to the other domes. What is all this noise, you know? Well, it turns out, actually, this is not noise. What happens is that this thing is actually periodic. If you go at the boundary between the Mott Insulator and the superconducting region, your system breaks up into islands which are superconducting and insulating. So if you actually measure the resistance, the differential resistance as a function of current bias and magnetic field, you have all these Fraunhofer-like patterns coming from arrays of Josephson junctions, where actually typically 1 or 2 junctions dominate, okay? So you have this phase coherence phenomenon, which can be modeled. You can look again for details at the paper, mostly with squids, you know, either symmetric or asymmetric squids. So they're typically 1 or 2 junctions that dominate this behavior. But the thing gets even better, okay? Graphene is a very high quality system, highly crystalline with high mobility. This means that we can measure quantum oscillations, Shinnikov-Dehas oscillations in the system continuously as a function of gate voltage. So in this plot, I'm showing the resistance as a function of perpendicular magnetic field and density. You can see here the superconducting dome there at small magnetic field. This is the trivial insulator state for holes, okay, when you completely fill the band. This is charge neutrality. This is the Mott Insulator state at half filling. And you see that there are several Landau fan diagrams coming out of different regions in this sample, okay? So this fan diagram and this fan diagram, these 2 fan diagrams, okay? The contrast is optimized for this. These are actually very beautiful fan diagrams, but we've optimized for this, which is the most interesting region. This fan diagram comes from the sort of Dirac points of this flat pancake. This one comes from this highly dispersive band, so this has very high mobility, highly dispersive band. Turns out that these 2 fan diagrams exhibit, you can look at what is the evolution of your Shinnikov-Dehas oscillations in this density magnetic field plot, and you can look at the evolution of the maxima or the minima, and it gives you what is the degeneracy of your Landau levels, okay? So both for this and for this region, you have a degeneracy of 4, which is not very surprising. I forgot to say at the beginning, but I think most of you are familiar with electrons in graphene have this 4-fold degeneracy, spin and valley. Yeah? So you have spin up, spin down, valley K prime. This also goes and folds into this twisted band structure. So we were not very surprised that indeed these fan diagrams exhibit filling factor sequences for 8, 12, 16, 20, etc. We have seen this in all of the devices that we have measured, by the way. However, there is also another fan diagram, which is coming out of the Mott state. So for this, you have to think about the following. I told you, we start from charge neutrality. We're filling our band. At half filling, there's this special thing, strong interactions, and the band gap opens, a correlated insulator state opens. Now, if you keep adding charge, in principle, this insulator state should disappear, and you should have the entire density of charge that you put from the beginning, okay? This is something which also, for those of you that are familiar with the Cuprate literature and phenomenology, that's also very puzzling in the Cuprates, okay? It turns out that our fan diagram in this region does not come, the lines do not come from this state, from charge neutrality. It looks like the density of electrons that we are adding is not that from the charge neutrality point. It comes from this insulator, from this correlated insulator behavior. Those lines come from here, which tell us that the quasi-particles that are involved in the transport, and also in the superconductor, this is occurring right above the superconducting dome, are quasi-particles as we dope this correlated insulator state. In the Cuprates, they say that the size of the Fermi surface that you can extract from these quantum oscillation measurements corresponds to X, the doping X, rather than 1 plus X, which is what you would expect from charge neutrality. Okay? So we have the exact same type of behavior, except that in the Cuprates, because the critical magnetic field for the Cuprates is so high, of the order of 50, 100 Tesla, depending which Cuprate you look at, you can barely access just the region above the dome in magnetic field. Because we have much smaller critical magnetic fields, much smaller critical temperatures, we can access effectively about 1,000 Tesla. So we can do this in a much more continuous manner, okay? So I'm not going to show a lot more about this thing, but one of the key things that happens here is that the Landau level sequence for this fan diagram is actually not every 4, as with here or here, is every 2, 2, 4, 6, 8, 10, 12. There's a halving of the degeneracy in this quasi-particles that come out of the Mott state. So now, as you may have noticed, I've steered clear of theory all the time, in my talk, which I think is good, especially when you talk about these topics. But let me point out here that a number of my colleagues think that this halving of the degeneracy could possibly, we don't have evidence, but let me just say it, could possibly be related to fractionalization, to spin charge separation. There are a number of theories that predict that as you dope a Mott insulator state, you should have a halving of your degrees of freedom, okay? But this remains still to be investigated. We can also measure, I'm not going to show it because of lack of time, but we can also measure here what is the effective mass as we approach optimal doping, et cetera. There are many things which have exact parallels with the underdoped cuprates, which is where all of this happens. Another thing that it's important to note is that here we can do this in a single, again, with gate voltage, in a single cooldown, in a single device, with the same disordered realization. To do this in the cuprates, it turns out that only some cuprates grow underdope. Different cuprates grow overdope. So you cannot actually look at quantum oscillations in the same material across doping. You have to change families of materials. So these small Fermi pockets in the underdope region are seen only in some cuprates. In other cuprates, they grow overdope and they see large, the 1 plus x rather than the x, okay, in the charge density. So we're hoping, that by being able to make this in a more continuous fashion, we can gain further insight. Now, as you have noticed, the maximum critical temperature that I have shown is 1.7 Kelvin at optimal doping for our strongest device. But usually the way to compare superconductors, what makes a superconductor very strong is not just what is the actual absolute value of the critical temperature, but how strongly is it superconducting given how many electrons you have in your system to superconduct, okay? So this is typically, represented in this type of plots where this is in log-log scale. You have a critical temperature and Fermi temperature or density, okay, and density you can convert from, for 2D or 3D. We're making them here 3D objects, we're converting them to 2D, okay? And this is telling you about how strongly coupled your superconductivity is. So, and this plot has been shown by one of the previous speakers with extra data points that I was glad to see, okay? Conventional superconductors, which are explained by weak coupling BCS, theory, are typically in this corner here. Okay? This is, for example, aluminum. Okay? Zinc, tin, niobium. As you get in this direction, let me plot for the people who are, as you go in this direction, I was told I had to use this mouse. Haven't been using it much. As you go in that direction, you go towards more exotic and more unconventional types of superconductors. Okay? Now, ion selenide, for example, is already a little bit weird. People have, it's not 100% clear exactly what's going on. You have here the heavy fermions. You have here the cuprates. You have here the iron pnictides. These are data points from our, both, this is for helium-4. This is for ultra-cold atoms multiplied by 100 million, both axes, just so that they appear here, okay? They can reach very much this BCB-CS crossover. So the stronger you go in this direction, the more unconventional typically, or the more exotic your superconductivity is. So magic angle twisted bilayer graphene happens to be there, okay? It is among the strongest superconductors that exist, okay, in the strongest coupling. Only iron selenide monolayer on STO is a little bit, higher. Now we can tune this with gate voltage, okay? So we can go, vary the strength of the coupling, by varying the gate voltage. And this is something that points to a very peculiar type of superconductivity in this system. So now, let me just say a couple of words. So this is a new platform for correlated physics, which is based on magic angle, and I put here in brackets graphene superlattices, because it actually turns out that this is totally generalizable to any 2D material. You put any 2D material on top of another 2D material, and there's always a magic angle for which flat bands will occur. This can be for semi-metals, for semiconductors, for metals, okay? The details vary substantially, but there's always a magic angle, which will develop flat bands where strong correlations will appear, each one with its own flavor. If you put materials with high spin-orbit coupling, you put 2D materials which are, ferromagnets, already superconductors by themselves, quantum speed liquids, topological insulators. There will be always flattening of the bands at a magic angle. There will be enhanced correlations, and you will be able to hopefully study a lot of physics with this. For the particular case of graphene, but for many of the 2D materials it's the same, These platforms are very highly tunable. You have electrostatic control of the charge density. You have mechanical control of the twist angle by rotation, by strain, and in some cases, by some groups like at Columbia, even continuously, possibly. Everybody asks me, how can we increase TC, okay? Well, the magic angle depends on what's the interlayer coupling. So if we increase that interlayer coupling, the magic angle will rotate towards higher, I mean, the magic angle won't rotate. The magic angle will occur at larger angles, which will naturally lead to higher densities. And if the strength of the coupling is maintained, that will lead to substantially higher TCs, critical temperatures. We have all of the knobs that we have with nano devices and all of the technology that comes with 2D device nanofabrication. We can put local gates. We can, after all, this is an electrically tunable superconductor, which is also useful in itself for many things. Okay? So with this, I want to summarize, but I think I already took a lot of your time. For details, you can look at this paper. Please go to my students' talk tomorrow. There's also another of my students speaking later today, so you can please stay for her talk. And I want to thank you for your attention.
So we have time for maybe a couple of quick questions.
Okay, that's an excellent question. We're not sure because we do not introduce chemical impurities. We're always doping with gate voltage, okay? But some people have told us that some of the fluctuations that we see in the superconductivity, when you look at the details, seem to indicate that we are relatively sensitive, which is something which is expected when you have a non-S wave order parameter. But we don't have evidence to claim that, we're not doing a systematic study adding impurities. That's part of the beauty of this. We don't have to add impurities. We just add plainly charged density.
Maybe one more quick question.
You have tunneling gap measurement done on this system?
No. As you can imagine, that's one of the first things that we want to do. It's not trivial to do those tunneling measurements, but we hope to perform tunneling measurements to, again, investigate what possible are the parameters. And since you're asking, I had this backup slide here to do that, because I know there are many people in the audience. So people ask me, what is the possible, or the parameter for this thing? There are no calculations for this particular, for magic angle graphene superlattices, but there are many, there are hundreds of papers about what can happen for graphene, and also by Bilayer graphene. I'm not including citation here, by Oscar Wafek, I'm seeing him at the end, has also predictions for Bilayer graphene. It turns out that when you dope graphene with ultra high charge density, you reach this endpoint where you have a von Hopf singularity, and people have predicted superconductivity. In most of the, there are all kinds of other parameters predicted, but it seems like most people coalesce around this D plus ID chiral superconductivity, which is related to the triangular structure. So if somehow in the superlattice, which is also triangular structure, that aspect is maintained, it could possibly be this plus ID. But it could be also, I've seen predictions for P plus IP, S plus minus, S plus other things. So, it's very rich and has to be studied for these particular heterostructures.
I know there are many questions that want to be asked, but in order to be on time with this session, we have to conclude. So let's thank the speaker one more time.
Thank you.